Beneath the ocean's surface, miles below the waves, lies a hidden world of geological activity that few have explored. Deep ocean volcanoes, shrouded in mystery and darkness, are far more numerous than their terrestrial counterparts. While land volcanoes like Mount Vesuvius or Yellowstone capture public attention with their dramatic eruptions, the deep sea harbors an estimated million submarine volcanoes, many of which remain uncharted. These silent giants operate in an environment of crushing pressure, pitch-black darkness, and extreme temperatures, creating a realm that feels alien yet is intimately tied to Earth's systems. Unlike land volcanoes, deep ocean volcanoes are difficult to study, leaving scientists with limited data about their frequency, scale, and impact. Hydrothermal vents and black smokers, chimneys of mineral-rich water spewing from the seafloor, are vivid manifestations of this activity. These structures, often found along mid-ocean ridges, support bizarre ecosystems where life thrives without sunlight, relying instead on chemosynthesis fueled by volcanic heat and chemicals. Tube worms, giant clams, and eyeless shrimp flourish in these extreme conditions, offering a glimpse into the resilience of life itself. But these underwater volcanoes are more than just biological curiosities. They may hold the key to understanding shifts in global climate patterns. The question is, could these hidden fires, operating far from human eyes, pose a threat to the delicate balance of Earth's climate? This exploration delves into the complex interplay between deep ocean volcanism and atmospheric changes, revealing how these geological forces could ripple across the planet with consequences we are only beginning to understand. To grasp the significance of deep ocean volcanoes, we must first appreciate their sheer scale. The ocean floor is not a static landscape, but a dynamic system shaped by plate tectonics. Mid-ocean ridges, where tectonic plates diverge, are the planet's most extensive volcanic systems, stretching over 60,000 kilometers across the globe. These ridges are studded with volcanoes that erupt regularly, releasing molten lava that cools instantly in the frigid water, forming pillow basalts and new seafloor. Estimates suggest that 75% of Earth's volcanic activity occurs underwater, yet only a fraction of these events are documented. Unlike land eruptions, which are often accompanied by ash plumes and pyroclastic flows, submarine eruptions are muffled by the ocean's weight. Lava flows are quenched rapidly, and gas emissions are absorbed or altered by seawater. This makes them harder to detect, but not less significant. The 2011 eruption of axial seamount off the Oregon coast, for example, was only noticed because of sophisticated seafloor monitoring systems. Such events remind us that the ocean floor is alive with geological activity, operating on a scale that dwarfs most terrestrial phenomena. The inaccessibility of these volcanoes compounds their mystery. Submersibles and remotely operated vehicles, ROVs, can only explore small areas at a time, and the cost of deep-sea research limits large-scale surveys. As a result, we know more about the surface of Mars than we do about parts of our own ocean floor. This knowledge gap raises critical questions about how these volcanoes influence Earth's systems and whether their activity could trigger cascading effects on a global scale. Deep ocean volcanoes influence the climate through a complex interplay of physical, chemical, and biological processes. Unlike land volcanoes, which can directly inject ash and gases like sulfur dioxide into the atmosphere, submarine volcanoes release their products into the ocean, where they interact with seawater before potentially reaching the surface or atmosphere. These interactions can alter ocean chemistry, circulation patterns, and even atmospheric composition, with far-reaching consequences. 1. Gas emissions and ocean chemistry. Submarine volcanoes release vast quantities of gases, including carbon dioxide, CO2, methane, CH4, and sulfur compounds. While much of this CO2 dissolves into seawater, contributing to ocean acidification, some may reach the atmosphere, adding to the greenhouse effect. Methane, a far more potent greenhouse gas, can bubble up from the seafloor, especially during explosive eruptions or when methane hydrates, frozen gas deposits, are destabilized by volcanic heat. A single large eruption could release significant methane, amplifying global warming. Sulfur compounds, such as hydrogen sulfide and sulfur dioxide, form aerosols when they reach the atmosphere. These aerosols can reflect sunlight, causing temporary cooling, as seen in major land eruptions like Mount Pinatubo in 1991. However, the cooling effect of submarine volcanoes is less direct, as seawater often traps these compounds. The balance between warming, from greenhouse gases, and cooling, from aerosols, depends on the scale and frequency of eruptions, which remains poorly understood. 2. Ocean circulation and heat. Deep ocean volcanoes also influence climate through their impact on ocean circulation. Hydrothermal vents release superheated water, rich in minerals and heat, into the ocean. This heat can alter local water temperatures and drive upwelling, where nutrient-rich deep water rises to the surface. Upwelling fuels phytoplankton blooms, which absorb CO2 during photosynthesis, acting as a carbon sink. However, these blooms can also release dimethyl sulfide, DMS, a compound that contributes to cloud formation, potentially cooling the planet by reflecting sunlight. On a larger scale, volcanic activity along mid-ocean ridges can influence thermohaline circulation, the global conveyor belt of ocean currents that regulates climate. Changes in heat or salinity from volcanic activity could disrupt this system, altering weather patterns. For example, a slowdown in the Atlantic Meridional Overturning Circulation, AMOC, has been linked to abrupt climate shifts in the past, and submarine volcanism could play a role in such disruptions. 3. Geological feedback loops. Deep ocean volcanoes are part of a broader geological carbon cycle. Over millions of years, CO2 released from volcanoes is sequestered through chemical weathering, where minerals in volcanic rocks react with atmospheric CO2 to form stable compounds. Submarine volcanoes contribute to this process by creating new seafloor that interacts with seawater. However, large-scale or frequent eruptions could overwhelm this balance, releasing CO2 faster than it can be sequestered, leading to long-term warming. Another feedback loop involves methane hydrates. These ice-like structures found in ocean sediments trap vast amounts of methane. Volcanic heat or seismic activity could destabilize these deposits, releasing methane into the ocean and atmosphere. Such events have been implicated in past climate crises, like the Paleocene-Eocene thermal maximum, PETM, 56 million years ago, when rapid warming triggered mass extinctions. Historical data and geological records provide clues about the climate impacts of deep ocean volcanism. During the PETM, massive volcanic activity in the North Atlantic igneous province is thought to have released enormous quantities of CO2 and methane, driving global temperatures up by 5 to 8 degrees Celsius. Fossil records show disrupted ocean ecosystems and widespread extinctions, suggesting that submarine volcanism can have catastrophic effects. More recent examples are harder to pinpoint due to the difficulty of monitoring submarine eruptions. However, studies of mid-ocean ridges and seamounts suggest that volcanic activity is more frequent than previously thought. In 2015, researchers discovered that the West Mata volcano in the Pacific was erupting almost continuously, releasing gases and heat into the ocean. Such findings indicate that submarine volcanoes may be a constant, if subtle, driver of environmental change. Modern technology is beginning to close the knowledge gap. Seafloor observatories, like the Ocean Observatories Initiative, use sensors to monitor volcanic activity in real time. These systems have detected subtle changes in ocean chemistry and temperature linked to eruptions, offering a clearer picture of their immediate impacts. However, long-term effects on climate remain speculative, as models struggle to account for the variability and scale of submarine volcanism. The potential for deep ocean volcanoes to act as a global climate threat depends on several factors: the frequency and scale of eruptions, the type of gases released, and the sensitivity of Earth's climate system. While a single eruption is unlikely to cause immediate catastrophe, a series of large-scale events or a sustained increase in volcanic activity could tip the balance. One scenario involves a pulse of volcanism along mid-ocean ridges, triggered by tectonic shifts or mantle plumes. Such an event could release enough CO2 and methane to accelerate warming, disrupt ocean currents, and alter weather patterns. For example, changes in the AMOC could weaken the Gulf Stream, leading to colder winters in Europe and more extreme weather globally. Methane releases could amplify this effect, creating a feedback loop that drives temperatures higher. Another concern is the interaction between submarine volcanism and human-driven climate change. Rising ocean temperatures and acidification, caused by anthropogenic CO2, could make methane hydrates less stable, increasing the likelihood of volcanic-triggered releases. This synergy could amplify the impacts of both processes, pushing the climate toward tipping points. Despite their potential, deep ocean volcanoes remain one of the least understood components of Earth's climate system. Key uncertainties include: how often do large submarine eruptions occur, and how much material do they release? Without comprehensive monitoring, estimates are based on limited data. How much CO2 and methane reaches the atmosphere versus remaining trapped in the ocean? The chemistry of gas dissolution in seawater is complex and poorly quantified. How do submarine volcanoes interact with other climate drivers, like ice melt or deforestation? Models need better data to predict these interactions accurately. Addressing these gaps requires investment in deep-sea research, including more seafloor observatories, advanced ROVs, and satellite monitoring of ocean surface changes. International collaboration is also critical, as the ocean floor spans multiple jurisdictions. Deep ocean volcanoes are a reminder of how interconnected Earth's systems are. What happens miles beneath the waves can influence the air we breathe, the weather we experience, and the future of our planet. While they may not pose an immediate threat, their potential to reshape global climate patterns cannot be ignored. The challenge lies in unraveling their mysteries before their impacts catch us off guard. By investing in research and embracing the complexity of these hidden fires, we can better prepare for a future where the ocean AS depths play a starring role in Earth AS climate story. The question is not just whether deep ocean volcanoes are the next global climate threat, but whether we can learn enough about them in time to respond.